Hi everyone, thanks for coming. Today I'll be going over my final project. But before I begin, I want to give a quick introduction about myself. So, who am I? My name is Isaac, and I'm a former data analyst at United Airlines. I spent my time at United working on an internal app for 40,000 mainline flight attendants. There, I was exposed to numerous data science concepts like NLP when I was performing sentiment analysis on newly rolled out in-flight meals and products, or to logistic regression when I was trying to predict churn to maximize flight attendant engagement with the app. As someone who is super fascinated by these concepts, I decided to join Metis Data Science Bootcamp to fully immerse myself in the fast-moving data science field. At Metis, I was able to equip myself with numerous skills to prepare me for a career in data science, covering all sorts of topics, including linear regression, logistic regression, natural language processing, and the topic of my final project, deep learning. I have videos covering all of my projects available on my LinkedIn, but today I'll be focusing on applying deep learning to my love of music. So sit back, relax, and I hope you enjoy my presentation. On today, we'll be generating lo-fi music with deep learning. Just a quick disclaimer that I'll be playing music throughout my presentation, so if you're wearing headphones, you may want to turn it down just a notch or two. So, the first time I heard lo-fi, I was in my dorm room in college studying for a final when I decided to flip it on in the background. After about an hour, I immediately fell in love with this type of music. The subtle sounds created the perfect blend of ambiance and presence, allowing me to easily enjoy its sound without being distracted from whatever it was that I was working on. So what exactly is lo-fi? Well, lo-fi consists of three very simple elements. The first, aesthetic sound effects. This is my favorite part of lo-fi. The name lo-fi actually stands for low fidelity, meaning the music is purposefully low quality. It can be something very subtle, like the sound of a cassette tape rolling, or a vinyl crackle, like this. Lo-fi fully embraces the beauty and sounds that would otherwise be considered audio imperfections. Suddenly, my dorm room wasn't just messy, it was aesthetically disheveled. The second part of lo-fi is the melody and chords. Many lo-fi tracks start off using 4-bar samples and chords and melodies from various different genres, such as funk, soul, jazz, and hip-hop. Oftentimes, the melody is distorted to create a spacey, ethereal sounding effect. The spacey sounding melody, combined with a warm vinyl crackle, creates a very soothing and mellow sound that really defines this genre. The third element is a very simple drum loop, usually with a lot of reverb. Here, I used a short clip of the song Pure Imagination, made popular by Charlie and the Chocolate Factory. If you listen closely, you'll be able to hear the vinyl crackles and distorted piano in this sample. So you can kind of see how this type of music can turn slogging through an all-nighter into a relaxing 1 a.m. study session. After listening to countless hours of lo-fi throughout this bootcamp, I thought it'd be fitting to try and utilize deep learning to generate my own. I used 100 jazz piano songs from Doug McKenzie, a jazz piano instructor, who had tons of MIDI files of his jazz covers available on his website to download for free. Next, I had to convert my MIDI files into a numeric LSTM readable format. I used a Music 21 library, which read through each MIDI and appended each note chord restoration combo to an array. That array was then split into 100 note samples. I mapped the note chord restoration combo to unique numeric values, since LSTMs understand numeric data more easily than categorical data. Those 100 note samples were then fed into the LSTM for it to train by predicting the next note and comparing its answer to what the actual next note was. Before I talk about my network architecture, I'll go through a quick and very high-level background on what LSTM and self-attention are, since both were used in my project. LSTM stands for long short-term memory and is a neural network developed to allow prior inputs to propagate further into the network, allowing for the concept of longer-term memory. This is accomplished by adding a specific memory cell to the structure, which has gates that decide when information enters memory, is output, and is forgotten. You can think of this as the network deciding what previous concepts are more or less important when calculating what output to give based on an input. From there, the network bases its new answer off of the more important previous outputs. Attention is a more recent development that actually helps solve a core problem. Attention remembers the intermediate calculations an LSTM does, which allows us to attend to certain components of the input at any given instant and use those components to help generate parts of the output rather than just the final calculation. Let me give a more contextual example. When reading, humans don't actually read word to word. We take shortcuts in how we process the data by grouping things together and attending to the context of different words, and then making assumptions based off of that. RNN and LSTM make the assumption that things work sequentially. Attention doesn't. While LSTM and RNN wouldn't have misread this image, sometimes the solutions to complex problems in languages, such as music, aren't completely sequential. There are a lot of complex structures in music, like melodies, counter melodies, harmonies, chord progressions, phrasing, voicing, repeated patterns, etc. So we need the ability of attention to contextually understand the music being written and then help guide the LSTM in what it needs to remember or forget as time goes on. Both were essential to my project. For my final model, I fed the Music 21 array of notes and chords into a bidirectional LSTM layer, which fed into a self-attention layer, which fed into another LSTM layer. The second layer of LSTM was intentionally not bidirectional. I decided to choose these layers because I thought that after the LSTM and attention initially made connections with understanding the data, it needed another layer to further develop the ideas it discovered. Bidirectional LSTM differs from unidirectional LSTM in that you have the ability at any point in time to preserve information from both past and future, as opposed to unidirectional LSTM, which, as it runs backwards, only preserves information from the future. You can kind of think of this as trying to predict the next word in a sentence. Bidirectional LSTMs would be able to look at a sequence of words at the start of a sentence, as well as a sequence of words at the end of a sentence. Understanding the surrounding chords around each chord is equally as important, especially in jazz when there's a big emphasis on creating tension and resolution. There's a very common chord progression in jazz called the 2-5-1. And so bidirectional LSTMs would be able to anticipate common chord progressions by simply looking at the surrounding chords. I use categorical cross entropy for my loss function and RMS prob for optimization because that's what most RNN-based models use. I also utilize the dropout function at multiple points in my model to help prevent overfitting from occurring. After running my model, my network outputs an array of probabilities corresponding to the different notes and chords I inputted. The value at index X is the output array, corresponds to the probability that X is the next note. As you can see, the highest probability for the next note corresponds to D, so we choose D as the most probable class. Once I have my predicted note, in this case F, I remove the starting index A from the sequence, append my predicted note to it, and then feed it back into the network over and over again to get a computer-generated melody. And so here are what my sample sounded like as I trained more and more epics. This was my sample after 3 epics. So some very basic stuff here. You can't really hear a melody. After 10 epics, my output sounded like this. So here you can kind of hear that the melody is becoming a little bit more developed. And finally, this was my sample after 40 epics. You can hear that the melody is becoming a lot more developed and coherent. I took my 40 epic sample, sprinkled in some vinyl crackles and reverb, and added a drum loop. And with that, I present to you deep lo-fi, chill hip-hop beats to finish a boot camp to. That concludes my presentation. I had such a fun time with this project, and I hope you all learned a thing or two today, whether it was about neural networks or even just lo-fi. My contact info is below, and I look forward to getting in touch. Thank you.